Hello, everyone. I'm super happy to have Emilia today. So she's a PhD student at Saint-Étienne at the University of Jean Monnet. And she's going to talk about soft glasses with hard fillers, the structure, dynamics, and flow. We're really, really happy to have you here, Emilia. And yeah, if you have any question, you can raise your hand or you can also type it in the chat. We'll be happy. Emilia is happy to have your question during her talk. But if you're a bit shy, you can ask them at the end. No worries. And yeah, Emilia, you can start your presentation by talking a bit about yourself, and then you can talk about soft glasses. Thank you very much for being here.
Thank you. Well, first of all, thank you for inviting me, Leah and Michelle. I'm super happy to be here in the Hitchhiker's Guide to Rheology because I'm a fan of the webinar series for a little while now, and my turn has come, so I'm super happy. Well, I prepared this talk about soft glasses with hard fillers, structure, dynamics, and flow. So there's going to be a lot going on. So maybe I think the questions, we can leave them for the very end so we can just have all the stuff. And if you have pen and paper, write your questions, and it'll be a great discussion after at the very end, if that's fine. So I'll introduce myself. I'm Emilia Cruz Arias. I'm a second-year PhD student at IMP Saint-Étienne, like I was saying. And I did previously a master's in process engineering for formulation. So that's where I discovered physical chemistry, colloids, rheology. But it was more, let's say, scaling from lab to process. So that's really interesting as well. But there's a lot of questions that still remain of what happens in the lab. So I thought, okay, I need to go back to the lab and do a PhD. And here we are. So today we're going to be, starting my presentation with a Hitchhiker's Guide to My Life Now at our lab, IMP. So IMP is the Polymer Materials Engineering Lab that's shared between institutions in Lyon and Saint-Étienne, like you were saying, Université Jean Monnet. And it's located in the Department 42. I don't know if it's a coincidence or just the universe speaking.
Maybe.
In IMP STE, Saint-Étienne short. We are 42 members working in all sorts of research topics related to polymers. So going from chemistry, physical chemistry, structure and rheology, biopolymer applications, we have it all. So you can come and drop by sometimes and visit us. This is the lab, it's super nice. So feel free to join someday. So let's start with the outline of what this presentation is gonna bring today. So first I'll do a bit of context of what my project is a part of. It's part of a bigger project. So what my PhD is about, what system I'm gonna be studying, and also what is the question that starts the journey of my PhD. Then we'll get into the more experimental part. So how do we approach this question, and what experience I have done, and what are my first results? Actually, maybe I forgot to mention, but I'm just starting my second year of PhD, so I'll be showing you just the first part of this story. So stay tuned for more. And we're going to talk about how this first year I've been linking rheology to microstructure. So how I prepared the soft glasses with hard fillers, and then how we probe their microstructure, local dynamics, macroscopic dynamics, linking them to that microscopic scenario. And finally, we'll talk about conclusions and perspectives for the 2 years of PhD to come. So let's begin with the context. So as every PhD, the title is a bit long for the PhD subject. It's the shear-assisted assembly of binary colloidal mixtures with tunable interactions. It's part of a bigger project called Making Soft Solids by Shear-Assisted Assembly of Colloids. And here, what the title is already telling us is that, well, when we shear a material, when we induce shear in a material, we can assist some certain assembly of colloids. Now, let me show you an example from research of this group. They were preparing dispersion of high concentration of inorganic particles, of calcium carbonate particles at high volume fraction. And what we will see here is that the preparation protocol of a soft precursor material, so many materials that are hard are initially soft during the preparation. And this is one of the examples. So what they see is that the way that we shear the material influences their mechanical properties. So let's take a look. We have two buckets basically next to each other of the same dispersion, same volume fraction, same solvent. But the way that we shear the bucket and then we let dry the solvent will reveal a different inner structure. So we can see it through the fracture shapes that we see here in these images. So the bucket that was stirred in an oscillatory way, for example, reveals this radial inner structure somehow. And then the bucket that was stirred back and forth reveals this lamellar structure. So we already start to see that we can assist some certain assembly by shearing. There's a memory that remains in the solid particles that were dispersed in this soft material. So now that we have that context, we can start talking about these soft materials that are then suspensions, soft glasses. So what most people think when we say soft glass would be maybe something like this, which is what I used to think before, but it's not really what we mean. So let's look at what we mean when we say soft glass. And what we're talking about is this phase diagram. It's a phase diagram that has these two axes, so interactions and volume fractions that are involved. But let's focus now in just a dispersion of hard spheres in a liquid. So no interaction is involved. We're going to be in this region of that phase diagram to prepare the soft glass, and I will show you how that works. So you have this colloid swimming in the solvent. It's a liquid-like dispersion. We have chosen colloidal hard spheres. They can be moving around because of Brownian motion, for example. But then you start putting a bit more and more particles, and there will be a phase transition at some point, because actually at some point you put so many particles that you have a liquid to solid transition, and it's very sharp, it's very clear. And this happens because simply each colloid is surrounded by neighbor particles. So now the dynamics of that colloid that was freely moving in the liquid are frozen. And then it's an amorphous solid because there's no really an induced structure in this case. It's just frozen dynamics that occur by the caging of the colloidal particles, and it behaves like a solid, because if I look for a long time, even in a long time, the relaxation time will be longer. So nothing really moves. We have made a soft glass, so a solid that's amorphous, and there's no chemical bonds. It's just happening because of that filling, spanning space with colloidal particles. So now we can imagine what would happen if we tune the particle softness, because of course if we're polymer scientists, we're going to think, what if instead of putting the hard spheres, I put particles that are diverse, that probably can deform, can interpenetrate. So what we will see is that there's a whole range of particle types that we could prepare a soft glass with. And that can go from linear chain polymers to star polymers, microgel particles, core shell polymers. And then we will also see that because of this ability to deform these particles, the space will be able to be packed much more than when you had just hard spheres, because hard spheres, well, they have an interaction potential that diverges to infinity. When you bring them next to each other, they cannot deform, so it's just like impossible to make them compress, let's say. So what happens when you put these particles that are deformable is that you can tune this divergence of the viscosity with the softness of the colloids. So it's good to keep in mind this kind of scheme, because I'm going to show it again later. And what you can see here is that you have the filler fraction in the x-axis, and then you have the viscosity. And the viscosity, you see that at some point diverges to infinity, like we said, for hard spheres. So it's the glass transition. And also we can keep in mind this concept that we're going to introduce, which is C star, the contact concentration of particles. So meaning the concentration at which all the colloids are touching and are filling the space fully. But now, because we can prepare higher concentrations, because we can deform the particles, let's keep in mind that C star is that concentration at which they are all touching. So a good way to illustrate this is the case of microgels. Microgels of glasses. There's this really nice example by Charlotte Pellet and Michel Schwatre, in which, because microgels can be deformed, they prepare a microgel dispersion. And you can see that there's different concentrations. And here it's a frequency sweep. So it's already a rheology experiment in which we get G prime, which is the solid-like behavior, and G double prime, which is the liquid-like behavior or the viscosity of the material. So if we just focus in this first scenario, just sample A, you can see that, okay, conventionally, just as a reminder, conventionally the open symbols are the liquid-like characters, so the G double prime, and the solid-like character are the full symbols. So here you can already see that, okay, you're more liquid-like than solid-like, so you are below the glass transition. It's your colloid microgel swimming in the solvent. So if you put more of those particles, you already know what to expect because I already showed you. You have a phase transition. So now you have the solid-like character that's above the liquid-like character. And then if you put more and more, now you can start to pack the space in such a way that your elasticity starts to increase. So now you're not only are solid-like, but okay, you're very packed solid. And the case of microgels is great because maybe I forgot to mention, but a microgel is basically a little polymer that's cross-linked. So it remains a unit and it's fully swollen with solvent. But then that means that the microgel, depending on the pH conditions, well, it's a polymer. So it will more or less span the space depending on the conformation and the environment. So we can tune this system by pH, softness of each individual colloid by increasing more or less the cross-linking density within the microgel, for example, or even other stuff like ionic strength, temperature, or particle interactions. And now we're going to get into how particle interactions could have an impact. Let's take a look. So as a reminder, we're talking about a soft glass, but in my project, I'm adding hard fillers. And we ask a simple question. So if you have a soft glass and you add the nanoparticles in the soft glass matrix, so we already know soft glass is just the full space of microgels. How does the mechanical behavior change when you add the hard fillers? Will it stiffen or will it soften? And a bonus question, once we understand that, can we control that response? So a really nice example that is found in the literature is not exactly the same scenario, but let me guide you through it. So you're now familiar with this kind of representation when your elasticity increases with a filler fraction. And in the gray lines, well, this has been studied for years and years now. So the gray lines are models that show what would happen if you had hard spheres or hard spheres that are attracted with each other, the Gold model. Nevertheless, you see that some simulations that were done show that if instead of just having the particles, you have a polymer network in the space, so a continuous polymer network, and you have the nanoparticles, and these particles are, or the filler particles, are attracted to the polymer network, well, the way you're filling the space will shift to the left, let's say, to smaller volume fractions to diverge in terms of elasticity. You see that you make an elastic material much easier when you have this attraction between that polymer network and the hard fillers. So now, because we are going to prepare a soft glass with hard fillers, we want to keep that in mind and understand what's going to happen when we add to our microgel dense suspension, to our soft glass, the nanoparticles. Will there be an attraction that leads to a shift in the glass transition, for example? Or will we be able to tune the attraction between the particles at some point? But that's many questions that arise. So let's start diving into how we approach these questions. So we have chosen to work with a model system and to study the structure in rheology at first. So we chose a polyacrylic acid-based microgel, which is pH sensitive. I will explain to you why that's a super interesting thing for our research. It has carboxylic acid functions and is commercially available. Most of the time, I'll be working with that microgel in the glassy state. Now you know that it's a concentration above C star, so everything is touching. We have made a solid, an amorphous solid, and the microgels are characteristic length scales of, maybe a few hundred of nanometers to a few microns. And to that of glass, we will add the filler. So the filler will be hydrophilic silica nanoparticles of 200 nanometers. These are commercially available, and we chose this particle size because it's bigger than the distance between two crosslinks. So there will not be diffusion of the particle within the microgel. So that's our hard filler, and we want to put it everywhere to see what's going to happen in that space. And then the approach is to study the structure with the static SAS. So SAS is small angle scattering that will allow us to see the structures within. So we do neutrons, X-rays, and light scattering, but today I will be presenting those that are in bold. And we also will study the dynamics, so the rheology, but also the microscopic dynamics, such as the X-ray with techniques like X-ray photon correlation spectroscopy or dynamic light scattering. And the most amazing part at the end will be that we are able to bridge both by combining rheology, the microscopic response, and the microstructure understanding, so real SAX experiments that we have performed. So let's dive into linking the rheology to the microstructure. First, we prepare some classes with hard fillers. Let me guide you through how I do that in the lab. So it's actually pretty simple. As you can see, this is the preparation protocol. So we basically prepare the two colloidal dispersions happily swimming in water. So below that glass transition, so far it's just here in white is the silica nanoparticle dispersion. And in transparent is the microgel. You can imagine it's transparent already because, well, it's mostly swollen with the solvent. So it's water or water glycerol mixtures I've been using. I will indicate eventually. So what you can see is that you mix them vigorously, and what you get is a very homogeneous dispersion. It looks like, okay, the nanoparticles have gone everywhere, and the microgels are there, the two colloids are there. And here, this is still a liquid. Now we swell it, and this is when the pH tunability of the microgel becomes super interesting. We fix the pH at 7, and we obtain a homogeneous dispersion of nanoparticles in that subclass that looks like this. Really nice. Let's look at what's happening inside, actually. So what happens inside is that you have the microgel, and you're going to swell it, so go from liquid to solid transition that we've been talking about by simply tuning the pH. So the microgel, when it's in water, it's going to release some protons, so it will be an acidic dispersion, and it's at equilibrium with itself and with water. So what you see here is that if you add NaOH, well, you consume some of these protons, and then you're shifting the state of the microgel to a more, well, ionized microgel, so a polyelectrolyte that is now repulsive within itself. So now the microgel swells and occupies more space. And what you see here is a little snapshot of the rheology. So before you swell it, it's basically almost a Newtonian liquid. You see, you have no yield stress, you have a very low viscosity compared to when you swell it and you are at that pH, and you have a shear thinning like material that has a yield stress. So if you don't shear it, well, it's basically a solid at rest. So let's now see what's the impact of adding those hard fillers to that glass that we have prepared. So the first question is, will the nanoparticles shift the glass transition? If you remember that I showed you that when you add the fillers to in the simulations and you make them attractive, you do shift the glass transition. In this case, it's different because in this case, we see that we add the nanoparticles to our system. So we fix here we have different microtubule concentrations and a fixed nanoparticle content, and you see that without nanoparticles or with nanoparticles between these two microtubule concentrations, so 0.1 weight total and 0.15, you go from, well, the open symbols above the full symbols, so the viscosity dominant over the elasticity, to the other scenario. So you have now from your soft solid or your soft glass, which contains the nanoparticles, but there's no shift in the transition. It's still happening between these two concentrations. So now we take some characteristic parameters. Let's say I'm calling this the plateau modulus, but it's just because, well, for my experiment, I take these two parameters at low frequency, so T prime naught and T double prime naught. And for different microgel concentrations, I prepare with the same nanoparticle content just to make sure that things are looking like the example that I showed you from the literature. So you put more nanoparticle, more microgel particles, and you make your material a bit stiffer and a bit stiffer, but still the glass transition is happening between these two, and that's the case of the scaling for T prime and T double prime. This is what we see. So yeah, things are looking great so far. We have learned that the nanoparticles are not shifting the glass transition. Okay, we can move on now to maybe what happens if we put more nanoparticles, because we want to also explore that effect of the nanoparticles. So we fix the microgel concentration above the glass transition. We have a glass, and we increase the nanoparticle content from 1 to 5 volume percent. So from 1 compared to 5, we see that the elasticity remains pretty much unchanged, even though there's the presence of the nanoparticles. So this is already really interesting because you're putting solid-like material and your solid-like response is governed by the microgel. And then you see also a viscous dissipation that increases, which is expected because you're putting more particles in space. So there's more viscous dissipation by motion and friction with the solvent. So now we can move on to the nonlinear rheology. Okay, we know the scenario for the linear rheology. There's not much impact what happens if we make it flow. So our material, we said, is a characteristic Herschel-Bulkley material. So it has a yield stress. Here's the microgel alone. Again, fixed microgel concentration, and we increase the nanoparticle content, and we see that when we deform at a increasing sphere rate the material, it becomes easier and easier to deform it. So it intakes more and more deformation. It's completely Herschel-Bulkley, the sphere thinning. We put the nanoparticles and it remains the same. So there's no really a visible impact of the nanoparticles in the flow of the soft glass. These first results are really, really interesting because you can now start to imagine, okay, I have input nanoparticles that can be tracers of my structure, because when you prepare your sample, you know that they are there all around, but they are not impacting the linear or nonlinear rheology at first sight. So now we can imagine that we can understand the structure of our soft glass by just seeing the nanoparticles as tracers. So it's really exciting. Let's dive into the structure. So what is the structure of that composite glass? So the first thing you do is you go and you put your material in the microscope. So you do optical microscopy, and this is what I did in the lab. So here is no microgel at all. No nanoparticles at all. So you just have microgel. So well, you don't see much, and this is expected because it's mainly swollen with solvent and dispersed in solvent. So you don't really see anything. But you start putting more and more nanoparticles, and you see that something starts to appear. First of all, well, actually, the microgels start to appear. You start to see what you expect, these transparent-like or very clear areas, and then there's these dark areas around. But the nanoparticles are not supposed to be visible in the optical microscopy because of their size. As you can see, they're smaller than the visible wavelength. So what are we seeing here? Is that isolated little pockets of nanoparticles with within the dense suspension of the microgel, and you see that the more you put silica, the more they appear. So now you start to be a bit suspicious of, okay, what's happening there? What is that? How does that look? And we're gonna talk about how we understand the shape and the size of pocket, observing it with small angle X-ray scattering. So X-ray scattering is an experiment that we performed at the ESRF in the European Synchrotron Radiation Facility in Grenoble. And what we do, this is how the setup works. We have the X-rays incoming and irradiating the sample in a planar wave style. So the wavelength is 1 angstrom, so very, very tiny. And we have the material here. So here will be our sample. And we record the scattering pattern and the scattering intensity of this at different angles. So the different angles actually will give a different scattering vector, and we'll be giving us information about different length scales. So let's take a look at what that recorded signal is telling us. So the intensity of scattering, so IFQ, it has 3 main contributions. So it has the contribution of the I naught. The I naught is the intensity of the scatterers, given by the volume of one single scatterer times the number of scatterers times the contrast of scattering. And I will talk about this now because actually for the rest of the talk, this will be convenient, is that the contrast of scattering is hidden in here. And it just basically means the electronic density difference of your scatterer and its environment. So we already know that the microgel is polymer and swollen with solvent, and the electronic density of the polymer and the water will be much smaller in terms of difference compared to that of the silica nanoparticles, which is condensed matter. And what I want to show you here is that I have a little homemade experiment that I like to do to explain to you what you're seeing when you're doing these X-ray scattering experiments. So here I have some beads of hydrogel that I use to simulate the microgels, and I have input some particles that I use to simulate, let's say, the silica nanoparticles. And when you do the experiment of the X-rays, what you are seeing, thanks to the contrast of scattering, is basically this. So because the contrast between the microgel and the solvent is so little, you're basically seeing the silica. So every time that we're seeing X-ray scattering experiments, we're mostly seeing the nanoparticles. So now that we know that, we can go back to our intensity of scattering and what other information is giving us. So it's giving us the silica scattering, but it's also giving us the form, the shape, is given by the form factor, so this P of Q, and the S of Q, the structure factor. So the P of Q is telling us about the shape of the particles, and the structure factor is telling us about the way the particles are distributed in space. Because you can see that when you have many particles, there will be also a correlation of in space of the particles, and then this will give constructive or non-constructive interferences. So another little example that I like to use, because I put it here so that everything is super clear. When you have your X-ray experiment, it's like if you were in front of a pond all day and you were throwing inside pebbles, for example. So first you throw one pebble, and that's the experiment that we like to do at first. If we just put one scatter, what does the signal look like? And we record the signal, and now you can also keep in mind that this form factor appears when you only have one scatter, so when there's no structure to correlate. So there's no S of Q or structure factor, just one scatter, and you have these patterns that appear. But what would happen if now I throw two pebbles and I put them close to each other? There's going to be an interference, as you can see, in the scattering intensity. So that interference will be different depending on how many particles you put, also in what is the shape of your particles, and as well how far and how close you bring them together. So after one day in front of this pond throwing pebbles, you will understand that the patterns are telling you information about the structure in a reciprocal way. So if we keep in mind that this is how hard spheres usually look like in scattering experiments, we have the intensity of scattering that now we're familiar with. We know that this is the particles. And the Q here is giving us a reciprocal length scale. So the scattering angle is giving us here, if we go to very high angles, then very small length scale. And if we go to very low angles, we see the higher length scales. Okay, so now that we understand the X-ray scattering experiment, we can try to see that for our sample is white. So what is that? What does that mean? How are the particles distributed in space? Let's take a look. So the first thing that we do is that we have the microgels. Well, actually, it's the nanoparticles in water. Let's take a look. The nanoparticles in water are reassuring, because what I just showed you is how nanoparticles would look like in space. So we prepared a very dilute sample, and we do see that this matches pretty much what I just showed you. So, okay, actually, the experiment we have done, it's the red line, it's the measured form factor. So it's when we prepare the very dilute dispersion. Looks super similar to what we see when we have just hard spheres. Also, maybe I forgot to mention, but there were oscillations that are very sharp when you have a super monodispersed sample, but in this case, we see that we have a slight polydispersity that erases a bit the oscillations. So far, we're happy. Now our particles are looking like hard spheres, so that's great. We put a bit of microgel inside below the C star, so below the glass transition or the content concentration, and we see that the shape that we're observing here has remained pretty much unchanged. So, okay, so far we can imagine that this is what's happening. It's just colloids swimming next to other colloids that we don't see with the X-rays. We just see these, and they look similar to when they're alone. Let's put a bit more microgel. And now we definitely see something that has changed. And this is what scattering experiments are all about, see shifts in the structure. And there definitely is a shift in the structure here. If we look at the scattering intensity, at the low angles, which we said is a reciprocal big length scale, there's something bigger than a nanoparticle that's scattering. So the intensity has increased at the low angles. So what is that? Is that the pockets that we observed in the microscope? Okay, let's try to understand. There's also this kind of whale that appears here. So to get more information about the structure, we compute the structure factor, which is the ratio between the intensity of scattering and the form factor of that one scatterer. So, of course, if there's just one scatterer or very few scatterers, this is mainly flat. There's no structure, like we said. But now that we have put enough microgel to have a structure shift, so to form this bucket, because the particles have become confined in within microgel matrix, we do have information that's being revealed in the S of Q, the structure factor. So what we look at here is, well, initially at low angle, again, a high intensity of scattering. So that can give us already information about how many scatterers are there in the pocket. As well, we get this well, this or also called a correlation hole, that's telling us about the density of particles occupying a pocket, and this peak here that this peak here that shows what is the probability of being at this distance. So remember that the reciprocal of this is it's a distance. So at this distance, there's a high probability of finding particles. So we're gonna go and understand this later. But for now, let's put more and more microgel because we like to do this. We see that nothing pretty much changes until we arrive to 1%. There is a shift that happens again at 1%. The structure is now different. So again, we're discovering and unveiling different states of this soft glass through these experiments, and let's try to understand a bit more. So to do a little recap, how do the buckets look? And how can we combine the Sachs, so reciprocal space observations and direct space observations? So the very first thing is the distance that I was telling you, the distance at which is most likely to find the closest neighbor in the pocket. So T star will be 2 pi over Q star. So at that peculiar scattering angle, we have this peak that appears, which is close to, in reciprocal space, in reciprocal real space, close to 2 times the radius of a particle. So meaning that we're particles within that pocket are almost touching each other. They are very confined. Then we see that the number of particles, which is an apparent number of the aggregate, let's say, that we can compute by simply estimating what the scattering intensity here is compared to when there's just one particle. We can estimate that there's around 50 to 100 nanoparticles in these buckets. And also, because we know that this is the highest length scale that we can probe, that the pockets are around 3 micrometers or maybe a bit higher. And this higher microgel concentration revealed that there seems to be 3 states for increasing microgel content, actually. That there's the liquid state, the glass state, and a faceted state. Let's take a look into that. It's an interesting observation that we've done, but we only have that one sample that's behaving this way so far, so we would need to prepare a few more. But for now, just to illustrate how this would look like, is that when you increase the microgel concentration, you go from those particles swimming to those pockets in the glassy state to perhaps a faceted scenario where you have less particles in a pocket. Maybe then your dispersion is a bit better for some reason, because maybe you're compressing the particles. So that would mean that the pocket is compressible, perhaps. And also, you have the probability of being next to each other at the same distance, but a bit to the right. So meaning that a bit closer. So coming up for in future experiments, we will probe the dynamics of this kind of systems to see if there's frozen dynamics of these particles here cannot move, and actually we have indeed compressed the pocket. And we will prepare more samples at higher concentration of microgels. So here you can already see that the particles reveal different states of the soft glass itself. So they're very good to tracer candidates. What happens then if we add more nanoparticles? If we fix the microgel concentration like we did for the rheology experiments, and we increase more and more the nanoparticle content, we see that there's no dramatic shifts in the structures. It's pretty much the same story. Now you're familiar with this kind of representation. You know that when you see this, you're seeing a pocket within this microgel, and you see that the pocket becomes a little bit higher in intensity, so meaning that it becomes a bit bigger, perhaps. You can also go look at the structure factor and try to understand this, like I was telling you, this correlation hole that tells you about the population of particles inside the pocket, which is going in the sense of deeper and deeper for higher nanoparticle content. So that is already also telling you that the pocket is more populated, but pretty much it's a homogeneous structure that exists within the soft glass. There's no dramatic changes, and they become slightly denser. Now let's continue exploring different states of the bucket. So actually now we're going to talk about the local dynamics with X-ray photon correlation spectroscopy. So are those pockets dynamic? Because we know that the nanoparticles are Brownian, so they are in motion, and this is Robert Brown who observed for the first time that particles were moving by themselves, and it was really strange and not easy to explain. It took years and years, but the explanation actually is that the molecules in the solvent are bouncing around the particles, and actually, if your particles are very tiny, they're more easily bounced around, and if your particles are bigger, then it's harder to bounce them around. So then, just because of this information, if you irradiate, for example, a sample that contains this Brownian moving particles with a laser, and then you record the fluctuations of the scattering, you will see that you can get information about the size of your particles, for example. And this is the Stokes-Einstein-Sutherland equation that allows to compute a diffusion coefficient by just observing the intensity fluctuations. So intensity fluctuations of this laser, and then we build a correlation function, autocorrelation function. So in time, as the experiment goes by, your structure will be shifting and shifting in terms of position of the particles. So at some point, the particles will be completely at different positions, and everything will be completely different than it was. And just by seeing how fast this changes, you can get already an idea of what's the size of your particles and what's the type of diffusion. Are they Brownian particles? So this kind of experiments are very easily modeled with the Kohlrausch-Williams-Watts KWW model, which is given by this exponential decay, and they allow to obtain this characteristic decay rate, which is given by 1 over a characteristic relaxation time. So we're gonna call this gamma of Q, and let's go and take a look at what happens if we put our particles in water. And this is what an experiment I did here in the lab. So it's dynamic light scattering of silicon nanoparticles in water. So if we put a few of these particles, and we just do the experiment where we irradiate, like I showed with the laser, and see the intensity fluctuations, we get our auto correlation function, and we see that there's a characteristic decay. And then we go ahead and plot that characteristic decay for different angles, which allows to scale the whole thing and obtain the slope, which is the diffusion coefficient, like I showed in the equation. We get our diffusion coefficient. We get, thanks to that, the radius, the hydrodynamic radius of the particles. And we're very happy because it looks exactly like what we said in the very beginning. We said that our particles are around 200 nanometers. So this seems like, okay, they're around that size that we said, and they have a slight polydispersity. I did a master scissor experiment, which is in agreement with that. So, okay, I'm pretty happy that dispersion looks good. The particles are diffusive, and there's a characteristic nanoparticle diffusion time that's a few milliseconds, sorry. Now we go and ask if the X-rays can see this motion too, because the interest is to, well, we have these nanoparticles in the soft glass, but it was white, so it would be difficult to perform the experiment with dynamic light scattering. So we go and see with X-rays, which can only see the particles, no matter how much we concentrate the space with microgel. And then what we see is that first we do this simple experiment. So we do the X-ray photon correlation spectroscopy. So this time, instead of light, our beam is the X-rays. And again, we get the correlation time that we expected. We compute our diffusion coefficient. Everything is looking great. So here, compared to the previous slide, which was water, now we're doing it in water and glycerol, which is the solvent I used to swell my soft glass. So we see that we get pretty much the same hydrodynamic radius. Nevertheless, the diffusion coefficient is a bit different, but that depends on the viscosity of the solvent as well, so that is normal. We do have diffusive dynamics, so meaning that we have a scaling, like I showed in the previous slide, of gamma versus q squared, that's giving that the slope of the diffusion coefficient in its typical characteristic of Brownian motion. And now we do the experiment in the soft glass, and we want to know if those pockets are really moving inside, if the particles are moving inside of the microgel. So we have the microgel at very low concentration, and we see that the particles seem to still be Brownian, but we know that they're not in a pocket yet. But okay, they're being a bit slowed down because the characteristic time is shifting to longer and longer times. We put more microgel, and we see the same. We see that the particles will always be in Brownian motion and within the pocket, no matter the microtunnel concentration, actually. So we look out for that characteristic time and we notice that the particles have been slowed down with increasing microtunnel content. Now, because we have a really cool model that can model this exponential decay, we extract the characteristic parameters to try to compare the dynamics of these different regimes, so below the glass transition and above. Let's take a look. So first, I chose this other representation here. So instead of putting Q square here, the Q square is the power law that scales the characteristic decay rate with the length scales. Then I put some length scales here so that you can keep in mind that we're seeing different windows with the different angles here. So we're seeing higher dimension or length scale than the particle itself, and also something that's relevant to see the particle. What we see here is that when the particles were just in the solvent, they were pretty much Brownian. So there was this Brownian diffusion with a power law of 2. But then something strange starts to happen. So this is results that are fresh and we still need to understand. What the main takeaway is that we see that when we know that the glass transition is between these two, and when we go beyond that, we know that the nanoparticles have become subdiffusive. So which mechanisms govern those dynamics within the pocket is one of the new questions that are raised. If we do a little recap of this part of the talk, we will know that we now know that the macro and microsignatures of the glass transitions have been revealed. So in the rheology, well, there was not a lot of difference when the particles were there. Also in the microscope, we were able to see that there's something that appears. Thanks to the microstructure knowledge now, we know that we have revealed that there is indeed a glass transition here that's seen by just the confinement of these nanoparticles in pockets, and the dynamics go from diffusive to subdiffusive. So the particles are slowed down once they are caged in the pocket as well. So under repulsive interactions, because so far we see that there's no particular shift of the glass transition when the particles are there, the nanoparticles are confined in dynamic pockets within the soft glass matrix. Now we can link the whole thing, so rheology and microstructure. And what we do is that we combine the two. So we irradiate the sample with the X-rays at the same time as we do the rheology experiment. So the flow curve in the experiment is a flow curve that goes from high shear rate to low shear rate, and then again up. So it's a down-up experiment, then from a low shear rate to higher shear rate in a quad geometry. And if you see this part here is the rheology experiment, you're now familiar with this representation of the soft glass. So it's a soft glass that is flowing and has a yield stress. So at very low shear rate, it stops flowing. But what you can see here is that we have linked the structure at the same time as we do the experiment. And now, as we are going to the low shear rates, what you're seeing here, because now you're familiar with all these characteristic shapes, if you see your structure factor, you see basically that there is this correlation hole, and now we're going for higher shear rates, and the correlation hole disappears. So let's do it once again. So the experiment will begin now. We go from high shear rates, and here our structure factor peak is very flat. What is that telling us already? It's telling us that the probability of being close at that characteristic length scale, it's becoming lower, but that's not the whole story, because you can also look at this part of the curve, and what you see is that the mass of a scattering object at this length scale has remained. It's not completely flat like in the case of when there's just one particle here. So the particles are not just fully decorrelated from each other. There's still a structure. It's just that during flow, something is happening in the density of that pocket, actually. Now, let's see what we have concluded from this part is that the pocket is forming at low shear rates or at rest as well during the decreasing ramp. And this is revealed by the appearance of that structure factor peak. And the pockets remain during flow because there's not a collapse of the structure. There's a structure there. So a nice way to illustrate this is actually in a flight of starlings inspired. There's a book that talks about how, well, how when birds are flying or starlings are flying, they can have this different dimension appearance. So here what I'm showing you is just a non-controlled shear rate experiment that I did. So I just compressed a droplet of my sample between two microscope slides. And I just saw that in the microscope and I see that, okay, it's impossible to really know what's happening to that little dot. But now, thanks to the structure factor during the flow, we have a better idea of what's happening during flow. So the pocket remains. The pocket is probably deformable by shear, as we can see, because there are definitely changes in the structure, but it's not a completely collapsed structure. So to conclude and talk about a bit of perspectives we have for the upcoming experiments, well, what we have learned is that the microgels and nanoparticles are repulsive because there's no dramatic shifts in the structure when they come together. The nanoparticles assemble in pockets of finite size within the soft glass, and these pockets are dynamic. So we can probe the dynamics through the nanoparticles of this soft glass with these composites. The pockets are also deformable by shear. So there's many things we have learned that are all in link with this shear-resisted assembly of colloids because we have sheared the system to prepare it. And now by shearing it also during the experiments, we see what's actually happening when the particles are repulsive. What's to come is, well, the rest of the PhD, of course. What can we make the system attractive, for example, by inducing microgel and nanoparticle interactions or attractions that would be exploring a different part of the phase diagram. And now that we know very well how the structure and rheology look like when the material is repulsive, we can go ahead and dive into this complex area, right, with the attractive composite glass. And also, an exciting result for me would be also, can we freeze the pocket? So we don't have the dynamics for that sample that was showing a smaller pocket. I have not probed the dynamics of that sample yet, but coming up, we have an upcoming experiment at the synchrotron, so we will have more information to come. I want to thank you very much for your attention, for the comments and questions you will have. And thanks to my supervisors and collaborators for all their help and guidance, and for the funding as well. This is my email if you want to send me questions, of course, or comments. It's the very beginning of this really exciting adventure. So thank you, and I welcome all your questions.
Thank you very much, Emilia. Is there any question in the audience? It was super great. I loved your talk. Happy to see also where you come from the poster and now what you have been doing. So yeah, is there any question in a lot of bravo and claps, apparently. Yeah, is there any question in the audience? Don't be shy. Oh, the chat. Thank you very much. It's been a fantastic talk, pedagogical and clear and super interesting from Michelle. Hi, Michelle. Thank you. Well, I got some questions, but I don't know if other people had. No. Okay, I would have thought that maybe there was a lubricating state in your sample, but whenever you increase the number of particles, but apparently you don't have any moments where it lubricated. And also, I don't know if you mentioned it. Does your particle can go inside the PAA network or not? I can't remember if you talked about it.
Yeah,
It can,
actually, you mean if the particle can diffuse within the microgels
yeah.
networks?
Can they be absorbed or not?
So we chose intentionally the size of the nanoparticles to avoid that, but we do
Yeah,
have different sizes of nanoparticles to probe in the future. So we will be able to explore also what happens perhaps if you have smaller particles that can diffuse
yeah,
inside. For now, we're still working to really officially be able to say there's no possible way that the particle can diffuse inside, but for this we need to know what really is the crosslink distance or the distance between two crosslinks or the mesh size of the microgel. So these are
yeah.
experiments that we're still performing.
Okay. And have you tried also like under very, very large deformation, if you have like the fillers that can maybe reorganize or migrate or um, have you tried that or not at all?
Yeah. So for now, we do have other Rio Sachs experiments where we are seeing what
Yeah.
happens to the structure through the rheology experiment. But those would be, well, the high shear rate is already telling us about the migration of that pocket that actually remains like these birds that
Yeah.
are flying. And as we can see here
Yeah, they're moving like that. Yeah, I've seen that.
in the little video, yeah.
Yeah.
And then the other experiment is, which also joins your question about the lubrication. This is
Yeah.
really interesting because an experiment that would allow to answer this kind of thing would be the transition to or the onset of flow, right?
Mm.
So this transient regime. So we have done some experiments to probe this, and that would be
Yeah.
sheer startup experiments that I'm still working on understand well treating that data and understanding what are the key messages that we get. There's
Yeah.
really exciting stuff about it, so more to come. Stay tuned. But yeah, that
Mhm.
would allow to also ask, are the nanoparticles facilitating the flow, for example? Mhm.
Mm. Yeah, okay. Well, I'll stay tuned then.
Yeah.
Yeah, there is one question from Jose. Hi, I have a question. How are you able to do the rheology measurements at the same time that you obtain the shape factor? What setup do you use for that? And thank you for the talk.
Thank you. Yes, let me try to go back. Can you still see the slides?
Yeah.
Okay, okay. Let me just go back to that experiment. Indeed. So this
Yeah.
is it's a really cool setup because indeed you are doing the experiment at the very same time as you're recording the scattering intensity fluctuations because you have a quet geometry that's a quartz. So we choose that the geometry and the beam goes right through the rheology experiment live. So all this is being recorded at the same time.
Um, Thank you very much. Jose, is it okay? I don't know if you heard the whole answer. Yes, he says yes, thanks. Well, thank you very much. Um, I guess that you can send the also the questions by email if you want. I guess that Emilia will be super happy to answer all of those questions. If there is no more question, then I'm gonna stop the talk right now and very like I want to say thank you to you, Emilia, because I loved your talk. It was really pedagogical and it was like a class because I'm not at all from that part of rheology and I love the way you talk and I think you really deserve that prize you earned during the conference. So yeah, thank you very much. There's no more questions, I guess.
Thank
Uh,
you.
there is great talk. Thank you from Ud. And yes, great talk. Thank you very much, Emilia.
Thank you.
See you all next week for the talk, the class of Gareth McKinley. And I hope you will all be there too. So yeah, thank you very much, Emilia. And I hope to see the rest of your experiments and how it shapes the end of your PhD. Thank you
Thank
very
you.
much.
Thank you so much. Thank you.